about consequences of the Lakshmibai-Sandhya Theorem, but now we've traveled quite a bit of a distance from the original theorem, and I wanted to talk some about computers. Let me just review a little bit. So lecture 1, we were talking about very classical results on Schubert varieties, in the manifold. And lecture 2, we talked about 10 properties that were characterized by pattern avoidance. Lecture 3, we generalized that to all Coxer groups, and I hope you've gone home now and done all your homework. But the good news is you don't have to remember any of the notation. This lecture is somewhat independent of the previous 3. We're going in a new direction. And so here's the outline for today. I want to show you some of the tools that I use in my research on a regular basis. Some of them you may know, and some of them are hopefully new. But I'll talk about someone's online encyclopedia of integer sequences, the OEIS, Printed Tenor database on patterns, a learning algorithm for patterns that I use a lot, brief introduction to SAGE, and new work that Henning Altmarson has done on learning Mark-Mesh patterns. So the OEIS. I say that again and again because that's the way that I look for it online. OEIS comes right up if you type it in the source query. This is a collection of integer sequences started by Neil Sloan. He started this in the 1960s. And way back then, he started on paper but quickly moved to IBM punch cards for his integer sequences because the collection got relatively large relatively quickly. And he just kept them in alphabetical order, more or less. So he kept them in lexicographical order, really. And now it's become an amazing tool for researchers in mathematics. In fact, I would say a universal database of integer sequences. What's really wonderful about it is that lots and lots of people can add their sequences. And in fact, now it has 212,892 sequences. Actually, that's as of the last time I checked. When we check today, it'll probably have more. But what I think is amazing about this is integer sequences are independent of what language you speak and the notation that you use and the differences in how we might write up our theorems. So if you have anything at all related to your research that could be written out as an integer sequence, you can go to this database and find out what other people know about that sequence. It makes it wonderful for making connections between completely different topics. So this is a great tool, and I want to just show it to you. And I hope that you will contribute, because one of the most amazing things about this is since everybody is contributing, it's not just Neil Sloan anymore doing this, the database becomes so much more rich. So I have to switch over and see if I can get the web to work. Actually, while I'm here at the web, let me just show you my web page too, so that you can see where I've stored all these lectures that we're giving. Frank mentioned in his talk that you could look him up by typing the word Frank.
That was a joke.
I tried it.
It doesn't work. I said my surname.
Actually, I thought it kind of worked. It brings right up this definition of the word Frank in English. But I have a little party trick. You type Sarah in math.
Ooh!
Notice Sarah without an H. Actually, sometimes when I type Sarah with an H, I get Frank's wife, Sarah Witherspoon. Okay, so here's my web page. I've got a lot of wordy things here on my web page. But as I go down the list, I wanted to point out this ICER program that's going on too. In 2013 in the spring, I'm co-organizing a whole semester on an event at Brown University. It's on automorphic forms, combinatorial representation theory, and multiple Dirichlet sequences. Somehow we're trying to find common connections between number theory and Schubert calculus. So that's the goal of this semester. There'll be 3 workshops. One that might be most interesting for you guys is in March, so I hope you check that out. Here's my little essay on computer-assisted proofs, what's the value. And down here are these talks. Maybe can I correct one other thing that Frank said? He said I have moved on from Schubert calculus, but that's not quite true. Look, I have a recent paper here on K-share functions. That has something to do with Schubert calculus, doesn't it?
Sorry, I didn't mean to slander
But
I know this paper too.
good. So anyway, I feel I'm growing and including bigger things, and so many things can be connected to Schubert calculus. So here are the lectures, and I will add the notes for today's lecture as soon as possible. I put the pictures there and the references as I've been collecting them, and I'm going to add a third directory here for the stage code that I'm using today. Okay, so we go back. And what I wanted to go back to was the OEIS. So here's the way that this works. You type in a sequence and you hit search. I'll just use this one. It comes up with the number of trees within labeled nodes. That's a sequence. And if we typed in something like the Gornstein permutations, we want to know how many of them are there, let's say in S10. You could just type in the word Gornstein. And it's in here. That was working. There it is, comes right up. So there's the sequence 1, 2, 6, 24, 116, 6, 36, and so on. It's a relatively difficult sequence to compute those numbers, apparently, because it's kind of short, but perhaps you could add to it. Another thing that you might look for are how many factorial permutations are there. But the problem with this, of course, is that word comes up quite often, 2,435 times. So that's not such a great way to look up these permutations. So I tried a few other things, actually. I tried typing in Steve Butler's name. He has 75 things in here. And Marais-Boscu, can somebody say it? Marais-Boscu-Melou. I think that's the proper spelling there. She's quite prolific. She has 394 things in there, so that didn't work either. So what really works nicely, though, is you just go get some data, and you type in the sequence that you're interested in studying. So 1, 2, 6, 22, 89, 397. Yeah, that's the one. And that should come up. There it is. These are the factorial Schubert varieties. So having just a little bit of the data helps you quite a bit to index into this database. In fact, I don't even think I need the 379. It should still work. Now there's 14 results, so you have to pick through them. And so sometimes I do have to do that. I get as much data as I can and then look it up. So let me go back to...
So what's useful besides just finding links? Sometimes you can find, you see something on these papers that tells you to improve what you have as you think.
Well, I was going on to something like that, right. So let me actually point out just how much stuff is in here for these permutations, for example. Go back to 379. So this is really useful because I don't always remember what was the generating function for those things, but it's down here. In fact, when I put it into the paper, I didn't want to type it wrong, so I just cut and pasted from right there. And there's the beginning of the generating function, so you can see the terms. There's some code in different programming languages included in here. There are links to the papers that you should go look up. Right, so it's all in here for you as a tool for you to capitalize on. So what about the locally complete intersections? Let me just see if I can find those LCI permutations. Oh, sorry. Doesn't match anything in the database. So that's something you could add. I don't think it's in there. So this database is only as useful as people make it. So we'll have to add that. All right, so I wanted to go back to here. We did these searches. I put them here. Actually, I forgot to point out that the 3-2-1 hexagon avoiding permutations are a good one to try, and it's because it does point to a nice generating function that comes up with them. There's a linear constant coefficient recurrence relation, actually, for those numbers. I completely missed when we were looking at that, and Julian West and Sekova found that, so that's something you can look up to. So here's a question. I don't know if you know the answer off the top of your head. Does the following formula have a closed form? well, that's one of those things you can get a little more data about, 16, 80, 288, so on. Go back over here. 16, 80, 288. Hope that's enough because I didn't remember the rest. The reason that I looked this up originally is because one of my colleagues at the University of Washington, Chris Birdsey, walked into my office and said, does this have a closed form? And I said, well, the standard thing to do would be to at least look it up on Sloan's and see if it does have a closed form or not. And sure enough, what a lovely closed form it has. N times n minus 3 times 2 to the n minus 2. And this was the beginning of a collaboration. And we proved this. This is not too hard to prove, actually. The reason that he was looking at that sequence at all is he was counting the number of permutations with a certain set of peaks. So the peaks of a permutation are the places where Wi is bigger than its two adjacent neighbors. So 1, 3, 2, 5, 4, 6 has a peak at 5 and a peak at 3. And he was interested in counting exactly the ones that have peaks at 2, 2 and n minus 1.
Sorry,
So
if you input this formula to Mathematica, then
it proves
most
it.
probably it will.
That's right. So actually I did that. Then there was the second step, to put it in the Maple and prove the formula. But you know, it's kind of nice to do it by hand too, so it's not too hard to prove it. That was step 2 of the collaboration. It kind of goes on here for a second, so bear with me. Let me go back here. So here's the definition again of the peak sets. And I just thought I'd segue into this a little bit because peak sets do appear in Schubert calculus in some ways, and they're very prominent in terms of quasi-symmetric functions, which if you haven't studied them before, you can check that out on Wikipedia. Let's let capital P of S, comma n be the number of permutations in Sn with exactly peak set S. And we'll say that S is n admissible if that set is not empty.
You said that has a peak at 3 and at 5, but did you mean 2 and 4 positions?
The numbers 3 and 5 are the peaks, but right, they're in positions 2, 4. Good point, yeah. And actually, historically, people have been doing work on these things for 100 years, believe it or not. It's amazingly rich literature, I found out. And they did it in terms of numbers, but I think it's better in terms of positions, the way I've been doing it. So the result of this collaboration is now a nice theorem with Chris Birdsey and Bruce Egan, just about to be put on the archive, but I've been postponing it while I'm working on these lectures. And the statement is that actually the number of peaks, the number of permutations with a given peak set is always 2 to a power times a polynomial function. So the power of 2 is very explicit. It's just 2 to the power n minus s minus 1. S is the number of elements in the set. And this polynomial has degree, which is exactly the maximum number that appears in s minus 1. So that's I sub s minus 1. There's a little bit of a case you have to consider for the empty set. It doesn't quite follow the rule. It's just 2 to the n minus 1. So the reason we thought to even write this down is there's a very nice formula for counting the number of permutations with a given descent set. And it has a determinantal formula that can be interpreted in terms of lattice paths. There's a lot of things done on that, but it's kind of funny that this was missing from the literature. So one corollary of knowing that you have a polynomial there is that it makes it very easy to get a computer proof of certain identities. So the corollary that is useful here is that if you know that the degree of a polynomial is some number, then one can compute the first few terms of the sequence and then use a method called finite differences. It's on par with calculus, but for finite sequences instead, discrete sequences. You just take the sequence and then you take all the differences between 2 adjacent ones. So I have an example of a sequence in the case where we look at the peak set 2, 4. So first, we calculate the number of permutations divided by the factor of 2 to the power. And you get the sequence 4, 12, 25, 44, 70, 104. When you take the first differences, you get 8, 13, 19, 26, 34. You see how to do that. You just take the first minus the second minus the first, the third minus the second, and so on. And you do it again, and you do it again, and you do it again. And if you have a polynomial function, you eventually get all zeros. And the interesting theorem that comes up in Richard Stanley's Enumerating Combinatorics Volume 1 book is that the polynomial can then be expanded in the basis n choose k very nicely The coefficients are just the numbers you see in the first column. So all you need to do to get a computer proof of an identity now is to get the first so many terms of the sequence. So this proves it. This proves the formula for the case where S is just 2, 4. And now you'll have to go through one by one and see different formulas. Okay, so I'm very impressed with the online encyclopedia of integer sequences. As you can see, it's definitely been incredibly valuable to me in making a lot of connections. And in 2005, Bridget Tenner did something I consider equally miraculous. She put together a database of permutation patterns, because once again, those are independent of language, and they are independent of the topic you're studying and the notation that you're studying. The way that this works is that she's just collecting a database. These patterns should be listed in a lexicographic order, but once again, you get to enter whatever sequence of patterns you want to, and you just have a little bit of space where you can put some references. Everybody can contribute, and you can search it by keyword or by pattern. So let me just show you that. So, Bridge blocking my link. So here's Bridget Tenner and her database of permutation patterns. I can find it off of her website. And here's a pattern I could look up. Actually, why don't I show you the entire database first of all? This is the way I prefer to look at it, because it's not too big. It's not 212,000 yet. I hope it will be one day. But here's the way that the links, it looks like. You can see there are permutation patterns of various kinds and some references, who added them. There's a link back to the OEIS. Lots of different things have been added in here. So you can look for things this way, or you can also type in a particular sequence. So maybe 3, 2, 1 would work, or 3, 5, 1. Oops, I lost it. 3, 5, 1, 2, 4. Maybe that one didn't come up. Let's just look for this one then. 3, 2, 1. Sure, that's in there. So it's nice and easy. All kinds of things can come up. So I hope that you'll consider adding something to this database as well, because it's doing the same thing. It's making connections where you might not have looked to find them. All right, so I go back to this. All right, so one of the ways that people can find new permutation pattern sets is just by taking any definition at all that's related to permutations and asking for the minimal permutations that are missing from this set. So you have a collection of permutations to find somehow which ones are missing. Well, here's an example. I have some permutations. Can you see which ones are missing? How would you define this set by pattern avoidance? I think you can see them all. So what's missing? What's obviously missing? Good. Okay, so does anything in the bottom contain the 3, 2, 1? No. Okay. So perhaps this is the 3, 2, 1 avoiding permutations. But there's some other things that are missing also. Do you see anything of length 5? No, they're missing too. This is the set of permutations that are missing 3, 2, 1 and all the length 5 patterns. And so we just learned the patterns, right? So here's the algorithm that I use whenever I come across a new definition. Let me just walk you through it because you can program this too. It's very simple. So if you have any Boolean function, that just means it returns yes or no, or 1 or 0, however you like to represent that. It acts on all permutations, so I'll index it by s infinity. So you start off the algorithm by having some set, let me call it B, that's the empty set. And then you loop for each n between 1 and some large enough number so it doesn't blow up your computer. Then you do, for each permutation in Sn, you check to see if the function f of w is different from a side function that I've written called the void patterns. And then check to see if w contains any of the patterns so far in B, the bad patterns. Well, you should have these two be the same, right? That's what the goal is. So if these are different, it gives you different answers. Then you want to check to see if f of w actually is 1 or true, it has the property. Well then, if it has the property, but it contains a bad pattern, that's the bad case where pattern avoidance isn't working, so we're putting on no classical pattern. And if not, then we're going to check this. It must be the case that f of w is equal to 0, so we'll add w as a new minimal bad pattern. Right? That's the algorithm. Is that clear what to do? You just keep going. And the way it works when it does work is that you're going along for a while, you're seeing patterns, and then you stop seeing some patterns. You stop getting new patterns. Right? Hopefully there's some period of time where you're doing like S8, S9, S10, you're getting no new patterns at all, so you can go no further. So the way that I might check this is using Sage. So Sage is one other tool that, in my opinion, is just like the online encyclopedia of integer sequences and headers database. It's free software that everybody can contribute to, and lots of mathematicians are getting great mileage out of it for their research. So I wanted to shift over and show you a little bit of Sage. So this is the way Sage looks when you're already into it. I should show you the way you're going to start. So sagenb.org is a great place to start. If you already use Gmail or Yahoo or something else, you can even easily get a login, but everybody can get a login. It's free. You just sign up, and then you'll get to have a worksheet that looks like mine that starts collecting all your things. And one of the great ways that I think that people are using Sage is just by sharing code left and right. Sage makes it really easy to share. So I will have these worksheets available on my website, and you can feel free to cut and paste from them. So I thought I'd walk you through a little bit of a tutorial before I show you my learning algorithm in code. So this learning algorithm, I actually took a class, believe it or not, this winter. The first time since I graduated. I've always wanted to take a class. I thought when I got tenure I would start doing it, but somehow, I don't know, it doesn't happen very often. So I took William Stein's Sage class. William Stein invented Sage. He's sort of the one who's championed it, and now he's got a whole army of people working with him on Sage all around the world. And he was teaching this class. I thought it was going to be like an introduction to programming kind of class, but it turned out to be an introduction to Sage development. And it's very clear why, because Sage is under progress. It's not done, it's not like Maple, it's not as polished, but it's free, it's easy to share, and you can contribute and you can see all the code. So in the long run, I think there's a lot of great reasons to start using it, and now is a good time. I held back for a while, even though lots of people around me at the University of Washington were using it. I held back until it was in good shape, and I do think it's up to speed now. So one of the students in the class is Andrew Johnson. He's an undergrad at UW. And he was taking combinatorics at the same time, and he asked me what he should do for the Sage project. And I thought it would be great if he just had a little tutorial about how to use Sage with combinatorial things. So I'm borrowing from his final project. And there's some links on here if you want to look up on Sage how to do things related to combinatorics. There's a great package for that, the CombiNat package. And then for more general things, I listed here the four things that I'm finding most interesting right now. William Stein has a book on Sage. I like to learn to program from a book. And I know not everybody does. A lot of times people use tutorials. This is a good tutorial on Python because Sage is built on top of Python. The Dive into Python book is also excellent. If you haven't programmed before, then I think a good place to start is a book. But if you have programmed before, it's just nothing to learn another language. So just get started and start playing. I just found this new link, Interact Sage.math. This is really cool because there's all kinds of demos that you might show in class. They're being put together just like Maple and Mathematica have. But these are in Sage, and what's nice about that is that your students can use Sage on their computer at home. They don't have to have a license. So it's just there in case you want to check it out. Okay, so how does Sage work then? So like I said, Sage is just Python. One of the basic data structures in Python is a list. So here, what happened? My list is gone, huh? You know what? I'm going to just not bother to reevaluate too much in this because I'm afraid of what might happen. There's a few things that take a long time to reevaluate. But the list one should have been this list. And the way that you define things in Sage or in Python is with just a plain equal sign. So on the next line, we take the list and make it into a set. That has some different structure. And so we printed out the list one as a set, and one of the things it does, it collapses some repeated elements. So if you're interested in sets, you might actually try getting a little help on sets. And so if I type here, set one, and then a dot and hit tab, what's going to happen? Oh, I might have to actually define this. 1, 2, 3, 10, maybe that's enough. I'm going to change it. When you evaluate, you do shift return, or you can click on the evaluate button. Okay, there. And now you type the dot. And one thing I like about this is to get help, type the dot, hit tab, and here comes all the things you can do with sets. That's a pretty easy way to get help. So you can do all kinds of things, like you might just pick an element of the set. So set dot element. Oh, and element, right, good. Underscore as element. And then close it up. Oh, I could have tabbed or something, pick the element. Good point. Okay, and what about how do you get a range of numbers? Let's say 10 numbers in a row. That's just range 10. Notice down here when it evaluates, it starts at 0, Python. And then if you want the range from 5 to 15, that'll start at 5, but it only goes to 14. So it stops one before the end. Once we have some sets, you can take intersection, union, set differences, things like that. You could find all subsets of a set. And this is a really handy construction here. So if I was to list out all subsets of a set, I could quickly fill my memory, right? But this is actually automatically going to be an iterator for you, which doesn't create the list. It'll be a way to sort of do a first search through them all, creating them one at a time. If you wanted to see the help on sets, or the command subsets, there it is. I type return and I've got it right here. So it gives you a little example. Did you notice the way that I got help actually was, remember, subsets with a question mark? And it gives you some examples on how to use it. And I really am very happy with this command where you put in 2 question marks. So with 2 question marks, it shows you the code that it's using to compute things. And you can get the code on everything. Because it's handy to know what the algorithm is doing behind the scenes. So the thing to making an iterator is the yield command. It's not just as simple as a normal for loop. Anytime you use the yield, you're making one of these generators. Okay, and the help works the same on objects. Let me see if I've gone back up. If I define this thing called C, which should have just been right here. There's the subsets. Then I want to find out something about C. I could just put a question mark on that too, tells me what it is. And we can check the cardinality of the set and so on. And in here, Andrew put a lot of nice things like counting functions. Instead of using the factorial as we normally draw it, you have to type the word factorial. But there they are, some factorials computed for you. Factorial 5 looks good. Do you know factorial 14 factorial? That's one I always show my class because since I live near Microsoft, that's approximately Bill Gates' net worth. I always like the number 52 factorial too, for obvious reasons. But if you try to type in factorial -1, that gives an error. All right, and we've got following factorials. It's got binomial coefficients. It's got the Fibonacci numbers. It's, it's trying to be as functional as Maple. And then we get down here to permutations. A permutation can be represented as a list, course. But there's actually a class of things, like there's this class sets. There's a class called permutations. And so you can do permutations of all kinds of things. I'm going to evaluate that one too. Notice what happens here. If I just want to look at the permutations of 1, 2, 3, it lists out in the first row all of those 6 permutations. And the second step here, it's saying to list out all the permutations in S4. And voila, it does that nicely. I thought it's kind of cute. You can permute things that are not necessarily numbers. And if you do permutations on a word, like hey, what do you think it should do? It just takes all the letters individually and permutes them. So that's kind of nice that it's flexible enough to take whatever input you might give it. You can look at the permutations as a group, and when you do that, it's not going to actually spit them out necessarily. It's going to make another iterator out of them, and if you wanted to see them all, you'd have to do dot list. Great. Okay, so here is checking the number of permutations in S8, and instead of printing them out, just check that the number of them is equal to 8 factorial. That's good. You can even do partial permutations here. This is a nice example. I kept this after Alan's discussion with the partial permutations if you wanted to run through all possibilities. This is the permutations 5, 3 are exactly what we might want to look at. Permutation using the numbers from 1 to 5, but only of length 3. That could be very useful. All right, so you can check the number of fixed points of a permutation, the number of peaks, that's in there. And you can even do things with pattern avoidance. So this is a nice one too. So you can check in the permutations of S5, how many of them are avoiding 3, 4, 1, 2. I guess 103 of them are. And we could print the cardinality. We can check, yes, indeed, that is less than 120. And there's this command. If you have a permutation, among the many things that you can do to a permutation is to check if it avoids a pattern. So let me just put in one little note here to show you this. So if P is a permutation, I'm going to type P dot to see all the things that I can do to a permutation, because that's probably one of the more relevant things for you. Bruhat order is in there. You can do things in terms of cycle types, descents. You can do stuff with the hyperoctahedral group. You can find reduced words. You can find tableau. Boy, there's some things in here, I don't even know what they are.
So does quick order have weak order?
I would be really surprised if weak order isn't in here. Oh, weak, well, no.
Weak exceedance.
Yeah.
No, it doesn't have weak order.
Okay, there's something for you to do. Now that is the problem with free software, right? If you find something that's not in there, you can't complain about it. The mission is you fix it, right? Because it's a privilege that you get to use this free software and see all the code. The responsibility is that you're responsible to make it work the way you want. That's what I learned in class. Okay, and it's got set partitions, it's got Stirling numbers, it's got integer partitions. It's basically, things are in there. Sometimes you might have trouble finding them. And that is actually the point of having a document like this, is to help with the documentation, because it's kind of hard to find the things you might be looking for. It's got compositions. I wanted to show you a little bit. Now down here is what I started to add. So far I've showed you how you can use pre-existing code. But what happens when you have to write something yourself, which happens all the time. So here I was trying to compute the sums of the squares of the dimensions of certain SN representations that come up, the ones with tabloids. And so to make a definition in Python, you start with the word def, and then you have the function name and its parameters in parentheses separated by commas and a colon. And the most important part of Python is this spacing out in front. So that has to be consistent. So if I had several different commands, I was going to run one right after the other, they would all have to have the same amount of spacing. If the next line depends on the previous line, you indent again. So here's some functions, and sure enough, we can compute these numbers. So that's a beginning piece of code that you might work with. I put this in here too, because this might come up for somebody. I didn't write most of this. I grabbed a version of RSK off the web that I found as I was searching around, and I learned some things just by looking at this. It's again an iterator kind of thing, and they did some cute functions like with bisect that I didn't know about. But this will give you both the P and the Q tableau of permutation under the Robinson-Shensteigen correspondence. So this is what a tableau looks like in this program. Not quite the way we look at it. It's a list of lists, but there it is. And I used this recently in my class because there was an annoying theorem that would have taken me a long time to write out on the board. And so I thought, hey, this is a perfect exercise for class. Go try and do a computer proof. So the mission was to give a computer proof that if two words are the same under the Univ class, then they have the same insertion tableau under RSK. A lot of cases for that to check. And not enough people did it, so I wrote up the solution. But let me give that as an exercise for you, okay? If you've never done a computer proof before, this is a perfect example of one to try. And if you get stuck, then you can read this. I tried to write it up as nice as I could, and the proof base is just, it's right here. You run this code. You have to find all possible words of a certain length. You run them, you check to see what happens when you do RSK. The theorem is true. You knew the theorem was true anyway, but there it says, see, the verification is complete.
So what exactly did you verify this? You checked it for digits?
Yeah, so what I did is reduce it to the fact that I only need to check words at length 6 or something. Yeah. Okay, and then a little bit more on permutations, and then I go on to the next thing. So you can do all kinds of things with a symmetric group. When you want to generate a group, now this is getting into some more interesting stuff that Sage does on top of Python. And there's all kinds of category type things. And one thing you can do is make groups. So here, I'm making a group by giving some generators. You can, once you've got the group named G, you can do G dot and look at all the things you can do to that group. One of them is to take the order, one is to take the character table by conjugacy classes. And there they are. So here I wanted to see some eigenvalues of the matrices, permutation matrices, to see what they look like. If you want to compute Kluger coordinates, there's all kinds of nice things with determinants too. So it's a good place to get started, and it's kind of targeted towards you guys. So this worksheet is the one called Combinatorics and Sage Tutorial. Great. So I'm going to go back to my collection. And I wanted to come along to pattern avoidance and get back to the learning algorithm that I use. So you can do this too. If you have a permutation, there it is. And like I said, you can try doing p.tab and seeing all the things that we can do to a permutation. I think we already did that though. So one of the things in there is p.avoids, and you can give it a single pattern. This works nicely. It doesn't work when you do p.contains. That's not in there. If you want it, just write it. That's easy enough to write. If you want to look at the code, remember you do p.avoids and double question mark. And the code kind of takes you someplace, and you have to follow up on that. But when you need to follow up on something, it usually gives you a file that's somewhere on the web.
Well, interesting. It has a pattern, but
yeah, that's right.
So it is that they're just not called by the same.
That's true. That's true because, and actually they're pretty careful about being like only having one way to do something. So maybe I just didn't find it the way I wanted to see it. So one of the things I didn't find is how to avoid a list of patterns, so I had to write that. There's another function for you to just crib from as you're learning. And so if I wanted to check to see if 62541 avoids the two smooth patterns, nope, it does not. Oh, sorry, yes, what does it do? Is that true? Oh, 0 should mean no, it does not avoid them. And yeah, I guess that's right, 6251, right? Okay, what about does 2431 avoid the bad patterns? That one should. Sure enough, there it is. Here's a little test for the Boolean permutations. Remember, those are the ones with the Bach-Samuelson variety and the Schubert variety are the same. And nothing happens when you define something unless you tell it to print something at that stage, so that's a good sign, unless there's some kind of typo in there. And is Boolean 4231, is that Boolean? And that should be false, right? Because it contains the 3 to 1. Okay, so is a Boolean function. it returns yes or no. And that's something that I know I defined it in terms of pattern avoidance, but I could have defined it in a different way, and then I want to learn that. So here's the algorithm that I walked you through, written out in Sage code. So it's supposed to learn patterns, and capital N is the maximum number of SNs that I'm going to search through. My property is some function that I'm trying to test. And pretty much you can see the code looks a lot like the pseudocode, right? So you're going to take n in the range 2 to n plus 1. You should never look for patterns in S1. Do you know why? Because they all have a pattern from S1, right? So don't bother checking that. Here I'm going to print W just because I like to look at them. First of all, when I'm checking my code, you have to really carefully always check your code. And then it's going to go through and do exactly what I said to do. If my property is equal to avoid patterns from a list, good, I don't have to do anything. But otherwise, if that's not true, we're going to either give an error saying it's not classical pattern avoidance, or we're going to add a new pattern to the minimal list of bad patterns. So, okay, let me evaluate. And, well, I don't know if I even want to run these things. This one isn't too bad. Run that. And it's printing all the permutations, right? And, oh, here it found one that is not Boolean. So good, it's adding a new one to the list of bad patterns. And then it's not doing anything for a while. And then it finds another minimal pattern. And at the end, voila, you get the nice error message property is closed under patterns through S6. And here's the list of minimal bad patterns. If I don't want to see all that junk getting printed, right, I'm going to down here. I'm going to get rid of this junk by now commenting out my print statement. So that's a hash sign, a number sign. And there you go. So it did the run. And without printing out the extra garbage, you just see the patterns that got added. So that's the way I would code it up. And a nice thing in Python, if you want to time your function, just a % time on the front, we'll add that, and you can see how much time it takes.
That's not very fast.
Well, that's a good point, and that is a problem I got to get to. And I really, in my real career, I'm much more a Lisp programmer than I am a Python programmer. And Lisp is still winning by hands down in terms of the Sage code that I'm writing.
It's probably not Python, probably the Sage is.
Well, Sage is on top of it, right? But Python is interpreted, so it's never going to be super fast by itself.
Actually, so at least with Perl, we want to interpret it. Really quite surprised by that.
Well, I'm going to come back to speed in just a second. I just wanted to show you, the Kazhdan-Lustig polynomials are also in here. I'm going to come back to speed, though, too. These take a long time, so this is not the most efficient way to compute them, but you can do it for all types. Here's a few that I've calculated. At least this one is correct, 1 plus q. And we could define the KL2 permutations using this method, and we could start learning those patterns as well. And I didn't want to run this in front of you because it does take a while, but there we start to print them out. And through S5, this is all minimal patterns that are not in KL2. If you wanted to run this for n equals 8, I had to eventually truncate it and got tired of waiting. And it would be slow. I don't know if you could even find all of them through S8. But they're starting to learn the patterns. All right, so that's a little bit of an introduction to that. To Sage and to how to do pattern avoidance with Sage and with this learning algorithm. And clearly I'm inspired by doing some other things that are going on in terms of neural networks and machine learning when I'm talking about learning algorithms. So if you aren't aware that the Netflix problem is a really good example of a machine learning algorithm. So the Netflix problem is, I don't know if you're not from America, I don't know if you get Netflix. But Netflix is a company that rents you movies, and they try to figure out what movie you would like to see next. So they're trying to understand your favorite movies, and they have a certain amount of training data that they put online and ask people to find the best possible algorithm to fit their training data, and they were offering $1 million for this. So somebody actually won the money, so don't bother working on it right now. But Netflix, even before they put this problem out there, was doing a great job of figuring out what people like to see. So there's lots of nice applications of learning algorithms. This is just a little baby one, but it's fun to think about. Okay, so I'm going to go on and talk about the next step in pattern avoidance. There's some really nice things going on in terms of trying to put the various kinds of pattern avoidance that came up in our top 10 list into one umbrella. And there's 2 steps towards doing that. Brennan and Cleason came up with this idea of mesh patterns. So a mesh pattern looks like this. So you have a permutation, and you write down the permutation matrix. And you do it on a grid, so the ones can only lie at the intersections of lines. So maybe here, and here, and there, and here, and maybe that's good enough. And then certain regions are marked, labeled in the mesh. So this one might become a forbidden region. So let me see if this is 3. I don't think this is one that I recognize as anything in particular. You could mark that out, and you could mark this out, and you get some kind of pattern avoiding family. That's a mesh pattern. And then Henning-Oltnarsson added a little bit more to this and said not only could we have forbidden regions, but we might specify regions where we have at most 1 element, or at most 2 elements, or some other way of describing what happens in another region. That's a marked mesh pattern. And a nice step in the theory of pattern avoidance is a theorem of Henning-Oltnarsson, where he was able to take these marked mesh patterns and put them into a nice structure so that you can see the smooth, Lorentzian factorial, the permutations defined by inclusions, those are Schubert grades defined by inclusions, 3-to-1 hexagon avoiding are all described as marked mesh patterns. And you can see more easily which families are included in the next. So let me show you the picture from his paper, A Unification of Permutation Patterns. See if I can get this to come out in the middle.
Yeah, we must have killed the last part.
How do I kill that? Oh, like that? Okay, so here's his picture. Smooth factorial defined by inclusions, Lorentzian, and okay, he calls it 1, 2, 3 hexagon, but just notice that he's twisted all of them, I guess. He's got the permutations. Instead of 3, 4, 1, 2, and 4, 2, 3, 1, he has 1, 3, 2, 4, and 2, 1, 4, 3. So there they are. And you can clearly see that smooth is contained in the factorial, is contained in Lorentzian, and not the same. Defined by inclusions is sort of a different branch of the tree. So it's 1, 2, 3 hexagon. It's a different branch in the tree. I really like this way of describing the pattern zone, and I like when the combinatorics all comes together. So I think this was a very nice step. All right, I'll go back to the SAGE code, because now there's a question that comes up. Well, if this marked mesh patterns are interesting, then well, how do we learn a way of describing or characterizing a set using marked mesh patterns? This is a little bit harder than the algorithm that I've just showed you. So Henning and I were talking about this, and he's done a great job of putting together an algorithm that will learn marked mesh patterns. I better do it like this. So I'm going to sign into SAGE so I can show you. Great. So I also use SAGE just over the web a lot of the time. When I showed you that initial link to go and log in, what I like about that page is that you can go log into SAGE and you can use it without having to download any software at all onto your own computer. So you can just get started today if you'd like and try it out. There's sort of no commitment, right? You didn't have to download anything. But if you decide that you're really using SAGE a lot and you want to take it with you when you're on the airplane or something, you can download SAGE onto your computer. And just recently, before it worked beautifully in Linux, it worked okay on Mac, but there was some friction with Windows that was irreconcilable, right? And that just recently got fixed. So now I'm running SAGE. It only took 5 minutes to download. It's really quite good. So here's Henning's worksheet. And he has some code that's available on Dropbox that you have to load. And he's defined several various kinds of permutation pattern type properties. The factorial ones, stack sortable ones, these West 2 stack sortable ones come up. at the permutation pattern conference that goes on every year, popular one. I'm going to scroll down here. So here's some of the patterns that it found. And what was it studying here? This was clearly the 4231 case and this one, this marked mesh pattern. So which permutations are described by these two patterns? So it's something you recognize? They did discuss it. So the minimal patterns that this program found in this case are the 4231, and this could be described as 3412, where the 4 and the 1 have to be together in order to count as a bad pattern. So this would eliminate the 45312, and so this is just the factorial permutations that it was learning. So I'm not going to have much time here to talk about the algorithm that he's using, but you could probably reason it out to some extent on your own, right? How's it going to go? Well, you're going to start to generate all permutations, and whenever you find a new pattern where the property is not true, then you're going to add it to your minimal list of bad patterns. But if you find one later on that violates the classical pattern avoidance property, so it contains a bad pattern, but it has the property, then you have to go and start making a marked mesh pattern. And in that case, you say that it has the pattern, and then wherever it has an extra number, that would become a forbidden region. And if later on, you may even have to update your forbidden regions to have certain properties. You can see that this could get quite complicated though, right? Because in some sense, you have to think about all possible subsets of ways the mesh can get filled in. So I think it's pretty clever the way he's got this running. You can use it or crib from it or learn from it. But here's some other studies talked about. One of the nice things that's coming out of Henning's work is the characterization of when does a permutation insert under RSK to a hook shape. And that seems to be characterized by these marked mesh patterns too. Okay, so let me conclude with some open problems, I think in order of difficulty. So could someone please add the LCI permutations to the online encyclopedia of integer sequences? Seems like an easy one. I started actually keeping these things on my CD. Seems like a academic contribution. I did it as a joke at first to keep myself entertained because my CD is a little boring, but you know, I think it belongs on there, so you do that too. Start putting them on there, filter it out, especially if you're a young mathematician and there's not a lot on there yet.
Well, you have to watch out because hiring committees may not like such stuff. They may find that stuffing.
That's not stuffing. I mean, unless you had 40 pages of them. If you have 3 of them, it's not going to bother anybody.
I've certainly heard discussions.
Okay, send your application to me. I will appreciate it. I'm never on the hiring committee, but I'll tell them to look out for people like that. Okay, and what about these marked mesh patterns? This is a really brand new hot topic, in my opinion, and we need to figure out how much we can do with it. It's a tool. So one of the things that's always been stuck in my mind as something that we need to find a better way to describe are the way that Lakshmibai characterizes the tangent space bases for the other types B, C, and D. I mean, it's a perfectly good way of describing the tangent space, and I guess it's forced upon us. It's not just as simple as it is in type A. But perhaps is there a way to use marked mesh patterns to give those conditions in a better way? And this would require you to take the marked mesh patterns and convert them to sign permutations. And that doesn't really exist in the literature yet anyway. So there's definitely something to do there, and I think it would be a nice contribution. What in general is the analog of marked mesh patterns for other permutation pattern types, like the sign permutations, or could you, in fact, extend it all the way to Coxeter groups? That'd be great. There's an interesting open problem in combinatorics about this poset on all the permutations, where if you compare 2 permutations as U is less than V if V contains U as a pattern. And one of the things that's open in that field is to kind of find a Möbius function for it. So I don't want to just define what the Möbius function is, but it's sort of the inverse of just the containment relation.
Have you done some calculations of that?
Have I personally? No.
Or that?
People have. Actually, it's a pretty well-studied problem. Yeah. So I don't think that's so trivial. Actually, if you need a resource to look up on that, Bruce Egan and Peter McNamara have a really nice paper where they looked at subword order on just any word. It doesn't have to be a reduced expression or anything. You just look at all the words that are subwords of it, and there they do find the Möbius verbose function. So that's where I noticed this problem. Started thinking about it a little bit, but I don't know how to get at that. And then, of course, maybe the more important problem that I would like to say with this lecture, the whole point of this lecture is what else is out there that computers can do to help you with your research. So the online encyclopedia of integer sequences is a great idea. The database for pattern avoidance is a great idea. SAGE is exactly the same idea. It's a great idea because it's a way that we can all do our research and share with other people, and it makes it very easy when you're working with collaborators. One of the best tools in SAGE recently went away, but I hope it'll come back, and that was a little button on the right that said publish. So you wrote up your code, and you click the link, and it's on the web for everybody to see. And it had to come down just in the last couple of weeks because people were using it for malware that was pretty bad. So, every good tool has its downside. But hopefully that will come back, and it's still not hard to share, and I will share these tools with you, and just by giving you the file that creates the SAGE worksheet. But I have to tell you where the file is on the web as opposed to it being sort of a permanent resource. Okay, so I hope you will be able to find some other computer tools like that and think in your own research, what are the things that characterize your theorems that are independent of language, that could be written down in a computer format, that can be looked up more easily, so that we can find commonalities between theorems in different fields and different languages and different notation. It's a bit of an artificial intelligence question, but I think something more is out there, just like the type of geometric series and integer sequences and patterns. So I want to conclude with, again, a thank you to the organizing committee and scientific committee. It's been a great honor to speak among this group, to speak to you and with the other people in the field who have been giving some great talks. I'm particularly happy to be here in Osaka because people have been so kind to me when I say Ohayo gozaimasu every morning to them. And the food has been absolutely delicious. Oishi. Oishi, yes. So, my closing statement, arigatai, so omo imasu.